Thanks for the introduction. My name is Masoud Dialameh. I'm a researcher working at IMEC in Belgium on atom probe tomography and ion beam analysis. In this today webinar, I would like to give an introduction to atom probe tomography for those users or potential users of the project who are not familiar at all with the technique. The title of today's presentation is 3D elemental mapping with nanometer scale resolution using atom probe tomography. I would start with what is atom probe tomography and what type of analysis it can offer. Then I will briefly discuss some fundamentals of atom probe, starting from specimen preparation, going to the data acquisition and field evaporation process, and then the 3D data reconstruction, and of course the data analysis itself. At the end, I will come up with a case study being accurate compositional analysis of silicon germanium thin films within nanometer-sized semiconductor devices. So what is atom probe tomography? We are talking about a laboratory-based 3D microscopy technique. So this is, for example, a commercial tool available from Kamika. We are talking about a laboratory tool which occupy a lab floor size of maybe 2 eyes or 3 times more than scanning electron microscopy. Atom probe tomography is capable of 3D elemental mapping with sub-nanometer spatial resolution. In this example from literature, this is an aluminum alloy. You could see different grains of aluminum, grain boundary, which in each grain, so the orientation of the aluminum atoms, basically these blue dots are aluminum atoms, so one can visualize the lattice plane with the correct lattice distance. In this case, solute precipitant can be visualized, can be analyzed, the composition of them. There's a lot that can be done with atom probe. We are here to discuss that. But what makes atom probe special? It's a combination of sub-nanometer or nanometer spatial resolution with a very high detection or sensitivity. So atom probe is isotopically precise in determining different elements, and that can be a very light element starting from hydrogen to heavy elements, in theory, the entire periodic table. So if you want to compare this detection versus resolvable feature size, atom probe stands um, somehow at the bottom right of the figure. So in terms of spatial resolution, atom probe is quite close to electron-based, so transmission electron microscopy, not as good as transmission electron microscopy, but the strength is on the detection range, the sensitivity of the techniques, which is can be orders of magnitude higher. So to put atom probe in a nutshell, there are 3 main characteristic steps of atom probe analysis, starting from specimen or sample preparation. Sample should be prepared in form of a sharp needle with the tip radius typically below 50 or 70 nanometer. Then we load the sample within the tool, we do data acquisition, and then the next step is to reconstruct the data. And by this 3D data reconstruction, we mean to reverse project the 2D detected events in form of the 3D volume, reassembling the original specimen shape. Of course, here the accuracy of the next step being the full data analysis relies on how accurately the reconstructed data reassemble the original atomic arrangement within the specimen. This example, this is a silicon germanium quantum well. Once the 3D reconstruction done precisely, one can do variety of analysis. For example, 3D compositional mapping, quantitative analysis, trace element, grain boundary, segregation, solute cluster precipitates. One can determine size, composition, distribution, interface and intermixing, statistical analysis, cluster analysis, nearest neighbor analysis. Uh, yeah, there are quite a lot to be done and quite a lot imaging. Even some chemical analysis are now visible with atom probe tomography. Um, let's start with the some examples from literature type of analysis which can be done. So this is the one that I already discussed. So this is an engineering aluminum alloy. We can see different grains. We can visualize the grain boundary. One can study the segregation composition in the grain boundary. Precipitates can be visualized, can be identified, and also quantified. While we have near atomic resolution, we can have the different structures of the material, the orientation of, in this case, aluminum, the blue dots within each grain. Another type of analysis could be the interface. So in this case, silicon germanium silicon interface. This is a work from literature, benchmarking against STM, scanning transmission electron microscopy, standard technique for um, analysis of interface and intermixing. So what you see here with these markers is actually the one measured by atom probe, and the lines are basically the one from transmission electron microscopy. So one can study the intermixing and the interface using atom probe tomography. Of course, special care also required here, which will be discussed later in this presentation. Hydrogen mapping is another speciality of atom probe. In this case, what you see is a reconstructed atom probe data for a titanium molybdenum alloy. In this case, a segregation of molybdenum, so enrichment of the molybdenum at the beta phase grain boundary is clear, followed by this is the map of hydrogen. So one can also do semi-quantitative analysis of hydrogen and mapping of the hydrogen. Of course, this is very niche application and a special application also for atom probe tomography. Special instrumentation and expertise is needed, but it can be done. Another example is the precipitate size. So this is a review figure from different comparison of atom probe versus scanning small angle scattering, X-ray scattering and neutronic scattering, so kind of a benchmarking. So you see, so for very small precipitates, let's say below 2 nanometer, so atom probe quantification, or let's say structural analysis, deviates from that of SAX or SANS analysis. So, but for slightly larger, there is still a bit of deviation. This is showing that atom probe can do some um, uh, structural analysis, identify the precipitate size, but it's not the main strength of the technique. For precipitates below 2 or 1 nanometer, the accuracy of the technique could be questioned. So let's continue with how we can measure a sample, a specimen in atom probe. So the first step is specimen preparation. And by specimen preparation, what I mean is to place the region of interest, what we want to measure, on top of a sharp needle with typically radius of 50 nanometer. This is what we can measure in atom probe. The typical and most common sample preparation technique is using focus ion beam technique. So I'm talking about the dual beam instrumentation. So the region of interest is typically being first covered, and then the lamella preparation and lamella lift out comes next. Then once the lamella is ready, it can be mounted on top of a wire, tungsten wire, silicon wire, and welded to it. And then the other side of lamella gets loose, and then we get a chunk of material welded to a prepared wire. The next step is annular milling. So you want to mill down and prepare a taper shape tip. So this is done by annular milling patterns to this kind of donut shape pattern. So by changing the internal and external diameter of these patterns, we can engineer and prepare this nice tip, which still need to be cleaned. So the final stage is actually to remove the damaged area by the fib itself, or redeposition and so on. So we thin down the specimen using low energy ions. So in this case, we are sure that the damaged area, at least for certain materials, is only a few nanometer, and the core part of the specimen remains intact. Of course, depending on type of material, maybe other sample preparation technique might be needed when dealing with organic materials, for example. Deep coating is basically dipping a sharp pipette tip inside a solution, or even cryofeed might be needed. There are other tricks and tweaks to it. So sometimes people deposit a capping layer on top of the specimen for, let's say, for battery application and so on. So these, but those are, let's say, some specialities. Let's stick to the basics here. So focus ion beam is the widely used technique for sample preparation. Um, Once the sample is prepared, we load it into the analysis chamber. So this is the specimen. Typically, the operation temperature is somewhere between 20 to 70 Kelvin. We apply very high potential, DC potential to the tip. You're talking about some thousands of kilovolt. This is to create a very intense electric field at the apex of the specimen. And in fact, this is the reason we need to prepare the specimen in form of a very sharp needle, because the electric field is proportional to inverse of the radius. So with the small tip radius, we can create a very intense electric field. I'm talking about tens of volts per nanometer. So during the data acquisition, we would like to remove atoms one by one from the specimen. Basically, we consume the specimen and detect their identity on our detector. The way it works is based on a field evaporation process. So there will be a laser pulse or voltage pulse, basically ionizing uh, every individual atom from the specimen. So once the atom is ionized as released from the surface, it immediately accelerates toward the detector. We have a position sensitive detector, so we can detect the coordinates X and Y of the hit points. At the same time, using the laser pulse as a trigger, one can do time of flight mass spectrometry. So in this case, for example, this is a case of silicon germanium. We can identify different isotopes, different charge states, and we can do elemental analysis. So these are the two pieces of information, main pieces of information we need: the detector, the hit points, X and Y coordinates, and also the identity of the element. I would like to also briefly introduce the theory of field evaporation and how we actually remove the atoms from the specimen surface. Theory of field evaporation. So this is a thermally activated process over an energy barrier reduced by the application of electric field. So what you see here is a simple one-dimensional potential energy. So in the absence of electric field, the energy to remove one atom from the surface is actually the sublimation energy. While to remove one atom and also n-fold ionize it, the energy we need, so this Q0 is actually, um, um, yeah, the ionization is, we need to consider also ionization energy, of course, minus the work function of the surface. In the presence of electric field, intense electric field, this ionic curve bends. So, and the energy we need, QB, to ionize and remove one atom from the surface actually drops. And this is because of the classical form, because of the Coulomb interactions. So we need less energy to overcome the barrier and have one atom remove this from the specimen. It can be done by thermal agitation if the field is quite intense. So there are in fact two ways to control and remove atoms one by one from the specimen surface. One is to keep at the specimen at a certain potential and then apply thermal pulsing. So this is the laser pulse, or by applying a field. The probability of evaporation, or in this case, the evaporation rate, depends on the intensity of the field, um, the temperature we applied, and of course, um, the property of the element that we want to evaporate. So, so far I discussed the sample preparation and briefly data acquisition in Atom Pro. In the next step, we would like to dive in the 3D reconstruction. So Atom Pro is actually a tomography technique. So we need to reconstruct all the detected events in form of the 3D arrangement of original atoms within the specimen. For that, there are already some protocols and available reconstruction protocols. In this case, point projection model is a good example. So we want to take the 2D hit events on the detector and then place them back in a 3D volume. To do that, in the most deconstructed method, basically the sequence of evaporation are being determined. So we know that at the top atomic layer, there will be more field enhancement, so or charge concentration, let's call it. So those atoms evaporate earlier than those from the second layer. And of course, at the sides of the lattice, there's additional field enhancement or charge concentration. So we know that the probability of evaporation is also here for, let's say, add atoms or at the side of the lattice. So basically, these are the sequence that we, let's say, or even we detect. So when we obtain from the detector, we want to put them together and reconstruct them basically according to what was originally on the specimen. For instance, the first um, detected event basically belongs to the corner left, and then the second one from the another side of the lattice. So the sequence here is matters. There are other assumptions to it. So we assume that the apex of the specimen is hemispherical. Um, Evaporation is ordered. This is the case for homogeneous samples. So if there are complex in homogeneity to different elements within the specimen, this won't be the case. So material property should be known, density, specimen shape. So typically we need also guidance from scanning electron image of the specimen or some references to reconstruct its 3D volume. This works pretty well for diluted systems, or at least locally we can do quite good analysis as it is. While for more complex systems, for example, for multi-layers where there are elements with really differences in field evaporation, so the evaporation rate, for example, in this case, this is the reconstructed 3D reconstructed data from atom probe. We see somehow distortion in the data, while locally still the lattice plane might be resolved, but the overall picture looks distorted. And this is in fact because of deviation of the apex. This is a simulated sequence of evaporation. So deviation of the apex from initially hemispherical to, let's say, irregular shape. So the reconstruction model does not anymore match the original shape of the specimen during the evaporation process. This is the TEM image of the apex after atom probe tomography, which somehow reassemble the simulated tip shape at the end. For more complex systems, for example, this is a fin-fed structure. This is the atom probe tip prepared. This is silicon. At the side, we have silicon dioxide. So this is the reconstructed atom probe data. In fact, this is even more distorted. So the positive taper turned to the negative taper and intermixing, so from oxygen inside the CG layer and so on. And again, the finite element analysis indicated for the non-hemispherical apex kind of trajectory overlapping, trajectory crossing, and in this case, we expect to have high density zones and low density zones on the reconstructed data. This is also evident from the SEM image of the tip after the atom probe experiment. We see that this is not anymore hemispherical and is more flat on the top. So to resolve this, there are some advanced data reconstruction protocols being developed. They are, for example, they can be based on a fitting of different parameters and trying to improve the data reconstruction. In this example, this is a quantum silicon germanium quantum bulb as measured by atom probe, but then it can be improved, and basically the layer structures can be, let's say, more precisely reconstructed. There are even more advanced reconstruction protocols based on simulating the trajectory of ions, but these are really demanding in terms of computation. So many GPUs are needed. Sometimes the analysis might take many days. Nevertheless, for routine analysis, what is existing right now can be used, and some deep insight can be um, extracted from certain region of the specimen. Now that we know a bit about how atom probe works, I want to start with a case study on accurate quantification of silicon germanium thin films within semiconductor devices. The downsides in semiconductor industry resulted in more and more complex architecture. Currently, the technology node is based on silicon germanium, is intensively being used, and also silicon germanium is foreseen to remain still in the picture for the coming years. What you see here is the schematic representation of a nanosheet field effect transistor. Here we have multi-layers of silicon germanium. So at the end, the silicon germanium layers will be etched away, and then we remain with the silicon channel. But what is important is that during the fabrication of such a device, this, there is a high etch selectivity between silicon versus germanium. So depending on the concentration of germanium between this silicon germanium layer, the etch rate might vary. So this etch recess problem is very important, and we need to know the local silicon germanium composition and its fluctuation. We would like to use atom probe, and in fact, we use the atom probe for this application. We need to know basically the presence of any compositional bias. So atom probe quantification, of course, should be accurate here in absolute quantification. And the second step is about the uncertainty. So when in this, for example, a sketch, when we see certain 1D profile of the germanium concentration, what is the uncertainty of what we measured? We have carefully investigated both aspects, so starting from accurate quantification of silicon germanium, so compositional analysis. We started from a thicker silicon germanium layer. We did quite a lot of atom probe investigation, trying to understand the accuracy of compositional analysis of silicon germanium. So what you see in this figure is basically field-dependent quantification of germanium in silicon germanium. So depending on the experimental condition, being electric field in this case, we might measure different composition within the same, of course, the same layer. But the origin of this, let's say, quantification bias still remain unknown. This is quite typical for atom probe analysis, also other material systems. But what is important for this specific application is that if we take Rutherford backscattering spectrometry as a benchmarking to define the determine the composition, so the reference composition, we can adjust the experimental condition, being electric field, to operate in a region where we know that we can accurately quantify germanium within silicon germanium layer. Or this can serve as a calibration curve, basically to correct and improve the accuracy of those data points that we measured at lower electric charge, and then calibrate them back to the actual composition. In the next step, we also studied in detail the uncertainty of the measured compositional fluctuation. So here we need to be careful. We are dealing with an alloy. So for a compound, if we look to the local area, so nanometric range, so the composition of the material remains comparable or uniform across the volume. While in case of an alloy, in this case a random alloy, homogeneously, let's say well, let's say randomly distributed alloy. So we can have different composition at different region of the specimen. So this random disorder of alloy is something known, but operating at this resolution, we need to take it into account. The second aspect is the extrinsic of the material. It's the counting statistics of atom probe. In this case, I want to also mention that atom probe has a special characteristic. So we are counting atoms. So with a perfect instrumentation, there will be no counting statistics. However, the current detection systems that we have, they have a detection efficiency lower than 1, or let's say lower than 100%. So we in one of the tools that we are working with, we can only count 62% of the atoms. This is the and the other part basically gonna be lost by the microchannels. So this type of detection efficiency, starting with this, we lose randomly some ions. So this means that somehow randomness being introduced into the counting of the system. Hopefully a day we might get an instrument with 100% detection efficiency, and then there will be no counting statistics. Nevertheless, we can model it by a binomial distribution. This is what we have done. So we can analytically predict what would be the statistics, counting statistics based on the detection efficiency fraction of the element, and also the number of elements within the unit volume that we are analyzing. We have combined these two contributions, and we obtain an analytical expression to calculate how much would be the uncertainty on top of what we measured with atom probe. We experimentally and numerically validated this expression in two different atom probe instruments and different experimental conditions. By this, now we know about the compositional bias. We can put a number uncertainty on what we measured um, um, along the tiny nanometric size area within the specimen. This is the atom probe, the SEM image of atom probe tip, which was prepared from the device. So what you see here is basically three different fins here. So we have more than one device within the field of view at the bottom, but of course on top. So the reddish one is basically the silicon germanium. Maybe this is more evident from this more zoom in reconstructed atom probe data. What we are interested in is to probe the germanium composition along the fin, along this the silicon germanium layer. And this is the final result that we have obtained. Um, Here, to probe the potential variation of germanium composition, we selected very small unit cells. So we obtained this, let's say, fluctuation in the composition above 10%. But our analysis allows us to obtain and tune the voxel size, the unit volume, to have a meaningful or resolvable compositional fluctuation. So depending on the voxel size we choose, then we can already know which fluctuation we should expect. So given the error bar that we have, we can say that there is no systematic, at least, or we cannot measure any systematic fluctuation of composition within these CG layers. Of course, we can also um, measure the composition locally within this one specific device. By this, I would like to conclude my talk with three messages. The first one is atom probe can provide reliable 3D elemental mapping with nanometer scale spatial resolution across diverse material systems. The key strength of atom probe lies in combining ppm level sensitivity together with nanometer scale spatial resolution. Of course, there are quite a lot of challenges remain for analysis of complex systems, heterogeneous systems composing different materials, elements with different evaporation fields. There are reconstruction artifact, evaporation effect issues, tip shape, and so on. To apply atom probe for studying of specific material, um, we need to be careful. It's case by case specific, um, and requires quite experience and knowledge about that specific material system. So some analysis might fail at the very earliest stage of the preparation of the specimen, basically by damaging the region of interest, or throughout the measurement or the data reconstruction. But there are quite successful analyses in literature, and the field is evolving. New materials are emerging, and that was my talk, and the messages I wanted to convey. And I'm ready for your questions.